Before I start, I want to thank the organizers for giving us this opportunity to be able to present our talks. Today I'm going to talk about a project joined with Andrew Snowden. It's going to be a little bit more introductory talk. I'll be trying to give important definitions and the important result we obtained in this work. Okay, so as you can see from the title, I just want to start with the definitions of the increasing monoid. The reason I say definitions because I will define two versions. The first version is basically the big version. So when you just think of all possible injective order preserving maps defined on the positive integers. So the second version is the one that we will be referring most of the time by I as the set of these strictly increasing maps such that there exists some L where for all, actually I should make this as for large I values, the sigma just shifts the I by L unit L. So this is kind of the small version of the increasing monoid, but we will construct and define everything based on this one. So before I start the representations, I'd like to say a few things. I'd like to state a few results regarding this ink actions. So especially the ones connected to the commutative algebra is a commutative algebraist. So one can define, maybe I should say, commutative algebra perspective, right? And we'll see another connection with the commutative algebra throughout the talk as well. So the one main thing is coming from the action of ink, the big one, over the polynomial ring with infinitely many variables. Okay. So I'm just going to refer this just for simplicity, k of x. Okay. So the action is quite natural. You can define it by defining it on each variable like this. Okay. And then we can talk about ink invariant ideals. Okay. So one of the known facts is sim infinite invariant ideals are also ink invariant ideals too. And the opposite is not true. So the ink invariance is much larger set. But the nice connection is the orbit inclusion. Okay? All right, so there are two results I'd like to state before I move on to representations. And the first one is about, I just want to show this more like analogy in both versions, symmetric and the increasing. Maybe I should start with the sim one. So by Cohen in 67, and I hope I'm not wrong, so 87, it is known that this polynomial ring with infinite variables is sim Noetherian. And its generalization for the inked version is given by Nagel and Römer in 15. Is ink Noetherian. Okay. And in the talk, I'll try to introduce another Noetherianity perspective for the category of the representations. All right, so now we can start with the actual part of the talk. So I will give two definitions for the representation theory. So we will be working in two categories. One of them is for the graded modules. The other one is for the smooth. Most of the time, the entire work is very similar, and it will like go hand to hand simultaneously, but there might be some differences, different situations depending on the category. So whenever we encounter them, I will try to underline it. Right? So let's define the graded and the smooth modules. So the M is a graded I module. So whenever I say I module, basically I'm referring the representation of the increasing monoid. Right? So we say that the module is graded if we can write M as this, as in this decomposition, such that the action of sigma for any element in the ink I, it will send it to, it will be contained in this degree component. And specifically, if sigma fixes n, then sigma acts by identity on this graded component. Right? So those are the graded versions. And then we can define the smooth version too. So this is a smooth I module, right? If every element in the module is fixed by this submonoid, right? So basically this submonoid is such that it fixes everything up to n, right? So we define the graded and the smooth like this, and then we can write down the notation for their categories. So the representation rep I is the category of smooth I modules, smooth representations, and we will denote the graded version with this underline. This is the category of graded I modules. Okay. All right, so before getting into a little bit more structure, I just want to state one nice result, observation, which gives us a little bit more connection with the other categories. So we notice that this is equivalent to another category, the category of the OI modules. Okay, so now as the remaining part of the talk, basically as an outline, I just want to say I will introduce three important monomial modules in these categories, important objects that basically helped us to construct the results we obtain in this paper. Okay? So that's why actually I'm just gonna write this as proposition / definitions, because I will define them in the meantime. Okay, so first we will define a one-dimensional model, like graded module. But again, like you can drop the line and you can just imagine the smooth versions as well, right? So the simple objects in the representation, the category of the representations of the graded ones are the one-dimensional graded modules. So I will denote them as Bn with the underline. And again, if you want, you can drop the line and just focus on the smooth case. This is what we called simple modules. Right? So they are basically one-dimensional modules concentrated in degree n, such that this sigma acts, the elements of the monoid acts on it by identity. Maybe I should just say it's by identity if it fixes n and it acts by 0 otherwise. Okay? So the simple objects are exactly these ones. Okay? So every simple object are going to be like isomorphic to one of these one-dimensional monomial modules. Okay? And the second definition and the proposition, actually this time I'd like to emphasize the graded version. The projective, the indecomposable, objects of rep I are, again, the I modules we denote them by this, a to the n, and called nth principal module. With a basis consisting of elements like these with an strictly increasing index sequence. Okay. And we define the action on these modules naturally by these basis vectors. Okay, so now I'd like to list a couple important results, observations about these monomial modules, and then I will introduce the next one. Okay? So some remarks, some results, facts. So the first one is about the principles. So this principal modules are the injective modules as well. Injectives for all positive, non-negative integers. Okay? By the way, about these principal modules, we lose the projective property when you drop the graded version. So for the smooth category, we don't have projectives, but we still study the principal modules. So they are still important, but they're just losing the projective property. So the second remark is about the trivial representation. So it turns out that the trivial representation is this B0 is the trivial representation, and it is isomorphic to A0. and isomorphic to A02. Okay. All right, the third remark is we introduce an invariant for any I module. So let's say M is an I module. Then we were able to define a multiplicity notion. So the multiplicity of the simple module in like concentrated in degree n in M is what we referred as the multiplicity, nth multiplicity of M, right? So after introducing this definition, we had this result, right? So it turns out that the multiplicity of the trivial representation in principles are always 1. Okay? Maybe I should just say, no matter what like nth principle modules you're dealing with, the trivial representation will have multiplicity 1. Okay? So this is what, I mean, the couple of things I'd like to say about the simples. For the principal ones, that's the part we are going to go connect this again back to the commutative algebra. So the connection is basically coming from the basis elements, basis vectors of this principal modules with the monomials of the polynomial ring. Okay, so they are isomorphic to each other as a vector space, apparently. And we construct this by this map. Okay? So these are, remember, like, maybe I can start with this condition. And this is sent to a monomial of degree in minus n, which is constructed by, it's somehow like the gaps in the indices minus 1. Actually, this is the first one. And the second one is I2 minus I1 minus 1. And In is In minus 1 minus 1. Right? So this is monomial of degree n, In minus n. Right? So this connection brought us the Noetherian property of these modules. Unfortunately, I'm running out of time, so I will, I mean, I wish I could give a little bit more space, details about this, but using this, we were able to introduce some initial monomial structure, and then let me just give the proposition. Right? So it turns out that these principles are Noetherian objects. So whenever you have some ascending chain of submodules, it will stabilize in this category. And then this gives us the following result. So we have this locally Noetherianity for this representation category. Locally Noetherian. Okay, so last 2 minutes. So let me just introduce the standard modules, which is the third one. And then I can at least state its importance in this representation theory in this category. So we will first set a word, fix a word like this. So this is a word in 2 letter alphabets. A and B, right? And we can talk about the index set associated with this word. So the index set is defined by the following. So these are, like, again, as usual, strictly increasing sets, such that this difference is 1, has to be 1 if the word has the letter B in the corresponding spot. Again, assuming I0 is 0. So the standard module, which we denote as EN, as is the module associated with this index set. So it is like generated by all those like E sub I1 up to IN, right? So the importance of this is the following theorem. It turns out that these standard modules, first, they connect the principal and simple. Just imagine the word is just A to the N and B to the N. And the most important thing is they helps us to describe the Grothendieck group. So the class of these standard modules form a basis for the Grothendieck group. Again, similarly for the smooth case. Okay, so I already went a couple minutes over time, so let me stop here. Thank you.